Okay, so I will start. Thank you everyone for coming here today, listening to my talk. Today we're talking about the design of an AC to DC conversion system with only partial power being processed on the active rectifier. With active rectifier, I mean the type of rectifier we can control. We have control over it to regulate the output voltage. So I want to send my acknowledgments to Professor Banerjee, my advisor, and Patrick Wang, the undergrad who is working with me on this project since I think early this semester. So let me first, it doesn't move. Yeah, let me first try to motivate the reason why I'm working on this type of conversion system. That is known to maybe to all the people here that we are living in a more electric power demanding world. So for many applications conventionally driven by mechanical power, now people are trying to shift it to electric power. Especially in transportation electrification. So, for example, many navies around the world, especially America, Italy, and some other European countries, they are trying to electrify the fleet. For example, the DDG 1000 destroyer here, it could generate, capable of generating 78 megawatt of power. To give you a sense of how much this power is, that is sufficient to power about 64,000 homes in America. 64,000. So that is the trend of converting the conventional applications into electricity, using electric power. And another thing is we are looking into a more sustainable world. Renewable energy is a trend people are going now. And for renewable energy, wind power is very popular. So for example, London Array wind farm, it could generate 630 megawatt of electric power. And at this rated power, it could power like 600,000 homes in American standard. So what is the common theme between these two applications? The common theme I want to bring up is both of them will be improved if we allow the generator to operate at variable speed. So for example, in ship application, the electricity is generated by the gas turbine. And most of the time, the ship doesn't operate at 100% of the rated power. So the load could be go to maybe 0.4 per unit. And people have shown that the efficiency of gas turbine, if you allow it to operate at variable speed and at partial load, the efficiency, so you see the curve with the square mark are the efficiency at fixed speed, and with the circle mark efficiency at variable speed. So if you operate at partial load, for example, at 0.4, then efficiency could be improved by 25%. So this is for ship is saying that if we allow the generator to operate at variable speed, the net efficiency of the system could be improved. It's just freezing. And for the wind farm, people already also show that by operating the wind turbine at variable speed, we can also improve the yield of the energy yield of the wind farm. So the reason is, so if you look here, the blue curve is the curve, the power generated by the wind farm when you allow it to operate at variable speed. And the other curves are like the red, the blue, and the black are the energy, the power of the generated by the wind farm when you allow it only operate at fixed speed. So the advantage of variable speed is you can collect power over a wider range of wind speed, and as a result, the energy yield will be higher. So if we look into what technology will enable those systems operate at variable speed, so if we look at the architecture, the power architecture people are proposed for the ship, Then we have all the turbines here that rotate the generator, and generator operate at variable speed. And a way to collect all the power is you convert them from AC power to DC, and then you collect the DC power on a power system, and then distribute the DC power to the load. So in this application, we see that we always need like the megawatt scale AC to DC conversion system. And for the wind turbine, there are multiple power system architecture proposed for wind turbine. It could be 2-step up, 1 cluster step up, or turbine step up. No matter what architecture it is, you will always see an AC to DC conversion system attached to each generator. So again, we will see megawatt scale AC to DC conversion system here. So that motivates my work. So I will look into an integrated approach to design megawatt scale AC to DC power conversion system, considering multiple aspects, including power electronics, control, and also electric machine design. And the requirement I'm targeting is it needs to be modular and scalable, because I want to adapt it to like multiple power level. It has to be light and cheap, because that's what we want to have. It needs to be reliable. And the last 3 are specifically for ship requirements. So it needs a convenient grounding, the simplified control, and high survivability. In case a ship is under attack, it still be able to survive. With that, the rest of today, I will cover the proposed architecture. Then I will cover the system design, and then I will tell a little bit about the test bed we are developing in this lab to illustrate this concept. For the proposed architecture, we will use a permanent magnet generator as a electricity generator for the system. The reason we use permanent magnet is because it has high power density, so it can reduce the weight of the system. The second is the operating cost of permanent magnet generator is lower compared to doubly fed induction machine and some other types of generator, because it doesn't require the burst or the slip ring. So the maintenance cost is less for a permanent magnet generator. But here we use a permanent magnet generator in a more special way. We use like multi-port of AC power from the generator instead of a single port of AC power. The reason for going to multi-port, because then we can feed each port to one building block rectifier, and then we will series stack all the rectifiers together. The advantage of this is we can reduce the voltage rating requirement on each of the components inside the rectifier because of the series stacking architecture. So in terms of the converter part, we're proposing series stacking some active rectifier with some passive rectifier. The reason to have the active rectifier here is that we need to provide some voltage, DC bus voltage regulation capability. Without the active rectifier, the DC bus voltage solely depends on the speed of the generator. And if we operate the generator at variable speed, then the DC bus voltage will like vary as well if we don't have the active rectifier. So, and for the selection of the passive, we just simply use a diode bridge. And for now, we have a capacitor to filter out all the ripples. The reason to go with the diode bridge is because for high power, it is efficient. It is maybe counterintuitive, but the reason for diode bridge to be efficient at high voltage and high power is because the diode drop is not dependent on the current flowing through the diode, so it will stay pretty constant around 1 volt, 0.9 to 1 volt. And think about if you have application with the voltage about like 1000 volt, and the drop across one diode is 1 volt, so you have like 99.99% efficiency on a diode. Another plus point is it doesn't have switching loss, so efficiency will be improved as well. And the third plus point is it's cheaper. So if we look at the diode rated for 1000 amp and 1.5 kV, the cost for one unit maybe $125 compared to an IGBT of the same rating. The cost for that IGBT is around $350. So we have like 3 times cost saving using diode bridge. For the active rectifier, I propose to just use the 6 poles IGBT kind of standard, because here we are looking at the system architecture instead of simply the inverter architecture. Yeah, so here we are saying we have N active rectifier in series with M passive rectifier, and they're all connected in series to generate the net DC bus. Yes. So now we're talking about the design aspect of this system. So we have N passive, N active, and M passive. How should we pick N and M? That is the question I'm answering in the system design. So picking N and M is kind of maybe when we see this equation, then it will be simple. So the way we pick M and N is to minimize the voltage support requirement on the active rectifier. And the voltage support required by active rectifier will follow this equation, where we see K is number of ports out of the generator we are having. So we see there's a term that is independent of operating speed, which is a voltage that we want to maintain. And M is number of passive rectifiers we're having in the system, and that is the design choice. But the term of M have a product term with omega, which is the operating speed. So this term saying that as the omega is operating speed in per unit, it goes from 0 to 1. So it says that if omega decreased, the voltage support, the M multiply omega proportional to the voltage support provided by the passive rectifier. And the difference between the DC voltage we want to maintain and the voltage support by the passive rectifier is the voltage rating for the active rectifier. So I hope this equation is clear to all the people. So we want to minimize V active by selecting what is M. So we see this equation, V active is a decrease function of M. So to minimize V active, we just simply pick M as large as possible. Because it has K ports, we can pick M as large as K. However, we always need one active rectifier to provide DC bus voltage support, like regulation for DC bus voltage. So we will pick M equal to K minus 1. And if we pick M equal to, Kevin, it just, okay. If we pick M to the K minus 1, then this equation will become the voltage support by the active rectifier. So here we see this is actually a design equation, because the voltage support is a function of operating speed and the number of ports for the generator. So using this equation, we can pick what is K and what is omega. That is completely the design choice. So the next slide, we will investigate the dependency of this equation with respect to omega. So the take here is if you want to operate at a wider speed range, then you require more power to be, more voltage to be supported by your active rectifier. So for example, if in K equal to 3, you have 3 ports. If you only operate at fixed speed, which is omega always equal to 1 per unit, then you only need like 33% of power supported by the active rectifier. But if you extend omega to be 0.55 of the rated speed, then at this point, the voltage support required by the active rectifier is like more like 60 to 63% of the DC bus. The reason we picked omega to be 0.55 is to make a direct comparison to the system using doubly fed induction machine for wind generation application. On the next slide is the dependencies of the voltage support by the active rectifier on the number of ports of the AC ports. We see that the more AC ports we have, the less voltage required to be supported by the active rectifier. So for example, if we go this way, by increasing K, we see the voltage support will be decreased, however, at a diminishing rate. So this is another consideration. You can go to infinitely many ports to have lower voltage support, but as you have higher number of ports, you have to design the machine in a special way, and you will reach some physical constraint that you cannot increase the number of ports anymore. Yeah, so that is a two interpretation for the design equation. And next, I will talk about the test bed we are having. So for the test bed we are having is, we essentially just build whatever I proposed. And for the machine, we use 3 ports. The reason for 3 ports is, I don't remember why I go with 3 ports, but maybe because of the voltage level of the machine, I have to make it 3 ports instead of more ports. So we have two passive rectifier in series with a TI motor drive, and we use the TI motor drive as the active rectifier. And then we will go with the, okay, so I can talk about the cost-wise. The passive rectifier costs like $10, and the box costs $700. So it gives you a sense on how cheap, if we go, it could be really cheap if we go with the passive rectifier. And here's how the test bed is performed. We test it under 2 conditions, under load change condition and under speed change condition. So if you see at this point, the load increased from 1 per unit to 1.4 per unit. And the goal is to maintain a constant 1 per unit DC bus voltage. And you see here, the red line is a voltage of the passive rectifier, and the green line is a voltage of the active rectifier. So when the load change, the voltage provided by the passive rectifier will decrease, and at that time, the active rectifier will take the lead and compensate for the drop in order to maintain a 1 per unit DC bus voltage. And we do a similar test when the speed of the generator is changing. Here we see initially the speed is at 1 per unit, and then I drop about 10%. And because of the speed drop, the voltage support by the passive rectifier will decrease. And when the active rectifier see the drop on the voltage, it will increase its output voltage to compensate for the drop and try to maintain the net DC bus at 1 per unit. However, we are not satisfied with this result because we hope that it can maintain a really flat 1 per unit DC bus voltage in this condition instead of have oscillation here. So that is one of my ongoing item. So we want to improve the controller to achieve the flat DC bus voltage under the change in operating condition. And another item I'm working on is because we want to improve the reliability, and the weak point of the system is the filter capacitor here. So if there's a way that we can remove the filter capacitor and at the same time still be able to maintain the DC bus voltage at constant, then that would be helpful to improve the reliability of the system. So we are thinking about doing the active control to compensate for the voltage ripple, and I will touch on that. Okay, so we do active ripple compensation. Conceptually, how it works is we have the diode bridge here, and if you have the sinusoid input to the diode bridge, the output voltage Vp of diode bridge will have the ripple. About the magnitude is about 20% of the light to neutral voltage of the source. So here, because we don't have the capacitor filter, so the ripple just stay there. But what we have is we have the active rectifier here. We can actively control the voltage. So if we can come up with a control strategy, generate the negative of the ripple sequence on the VA here, which is the orange line, then both of them add up to the VDC to be constant. So if we could do that, then we will be able to get rid of the capacitor filter we used to have for the test system, for the system I'm building now. So can we do that? I think, well, I believe we can do that, because otherwise how can I graduate? Yeah, but if we think more conceptually on the active rectifier, it is like a power conversion device. So it converts AC power to DC power. And what control knob I have on the active rectifier is three switching function, QA, QB, QC, to control the switch of the IGBTs. And if we go like one more abstract level, what control knob I really do have is a 2 voltage reference signal, VRD and VRQ. And the power balance of this active rectifier is follow this equation. The left-hand side is the power you inject into the AC side of the rectifier, and the right-hand side is the power you draw from the DC side of the rectifier. So the two control knob I am having is VRD and VRQ. And I will need to design the controller. So I given a reference voltage, then it will give out the VRD and VRQ to track the reference. So if I give the reference to be the negative of the ripple sequence, then the voltage, the DC side voltage of the active rectifier will be like counterbalance the ripple sequence and make a net DC bus voltage. So conceptually, it sounds simple. However, we have some, I have achieved something to show, conceptually show the feasibility of this thing. So if you see here, the blue line is the diode ripple sequence, and I believe that is the orange line, but it looks red, it's okay. The red line is a voltage synthesized by the active rectifier, and then we add the two together. The yellow line will be the DC bus voltage. Ideally, it has to be flat, but we always have the difficulty matching when it suddenly changes here. So if any of you have a good know how to precisely track a waveform like this, especially when we have a sharp change, the derivative here is infinitive. So please let me know. You can make my PhD a little bit easier.
You get another problem.
Yeah, we have tons of problems to deal with. But I will be happy if we could solve this one first. Yeah. I think this is the end of my presentation. If you have any questions, just let me know. Yes. 27. Yes.
I see the output voltage is slightly less than 1 per unit.
Yeah.
Any reason for that?
Well, it is by normalizing. So here I send a command, I believe to be 82 volts, and the realization is a little bit less than what I expected to have. So it could be maybe the non-idealities in the system, or my controller is just not as good as I expect it to be. So yeah, there's room to improvement here. Yeah. Any more questions? Okay. So if no, I think Nate will continue the presentation on his work.
all this because I gotta find my desktop, which is over here.
Disappeared.
There.
What happens if you hit the Windows? Up one more. There, yeah.
It's over there. You got the drive.
Yeah, I got it. Cool. And then where do I put this guy? Just kind of here.
Yeah. You better spin.
Cool. Okay. Would you mind handing these out one at a time? Just kind of go that way. Yeah, whatever. Okay. Hello, guys. Today I'm talking about light bulbs, specifically LED light bulbs. I don't know how much you guys know about them, but this is kind of a topic that has more application, I think, with the modern consumer. And you guys obviously use light bulbs, so hopefully you can learn something from the perspective of LED driver design. Okay, so some of the goals of this research is we took a survey of existing consumer light bulbs, and if Sam, could you hold up the light bulb back? Just one of the light bulbs. Yeah, so it's that shape and size. So it's a 60-watt equivalent light bulb. Yeah, thanks. We took a survey of about 20 LED light bulbs. We took them apart. We took measurements, and we're trying to characterize some of the design trade-offs that are necessary when you make an LED driver as it pertains to industry. Specifically, we're trying to compare two different types of prevalent LED technologies. One is what I call matrix, which is what you're probably more familiar with. You basically have an array of little LED chips. The second one is called filament, and this is a newer technology. Usually you see it in stores under the name of like antique, or I don't know. It gives but it looks like a traditional incandescent bulb. So the selling point is, oh, this looks like old-fashioned kind of what you're used to, rather than these fancy little new LED bulbs. So anyway, that's an interesting technology because it isn't just something for aesthetics and nostalgia. It's also it is a technology that has a lot of improvements over the traditional one, which is why it's gaining more market popularity. And then the third goal was to identify the performance metrics by measuring these performance metrics and then looking at them and comparing bulbs, seeing the design trade-offs, and then hopefully eventually using that information to make informed decisions on our own LED driver design. Okay, so here's a quick history of lighting technology. Incandescent bulbs have been around for as long as electricity has been on the grid. Typically, when you see the 60-watt equivalent, what that means is about 800 lumens of light output. Incandescent bulbs have about 1,000-hour lifetime, so that'll kind of give you a comparison as we go down through these technologies. So then compact fluorescent lighting was introduced in the 1980s, and it's an older technology, but that's when it became prevalent in industry and for consumers. In this case, it takes about 13 watts to produce the same 800 lumens of light. So you can already see the quote-unquote efficiency gain from using this technology. And then on the bottom, we see the matrix LEDs, which first came around in the early 2000s. And in this case, it takes about 8 to 12 watts to produce 800 lumens. And if you look at the lifetime between the three, the lifetime increases with the technology. And that's part of the reason that it's gaining acceptance, is because it might not be cheaper, but it might last a lot longer and be a lot more energy efficient. Okay, so here's a couple facts, and the point of me saying these facts is I want to kind of give a gauge, or kind of give you an idea of where the LED market is going, just from kind of the facts of the past decade. So right now, the lighting and bulb manufacturing industry is around $1.5 billion, which is huge. But it's important to know that it's actually on the decline. And this is because incandescents aren't popular anymore. I think there's the government, at least in the United States, is saying that there was not allowed to be any more incandescent bulbs within the next 10 years. Like there's a deadline where all incandescents have to be exchanged with newer, more energy efficient bulbs. And so you have to think, okay, there's this huge industry. What happens to all those factories, all those employees, like all those businesses? What do they do to sustain? Do they just die away, or do they make a market change, a market shift? So in 2010, the DOE estimated that there were approximately 1 billion 60-watt incandescent bulbs in use. That kind of gives you a gauge of how many of these bulbs are out there. Like how many potential sockets can be filled with a light bulb. And then in 2009, there were around 400,000 LED light bulbs installed in the U.S. And then by 2013, that had already gone up to 20 million. I don't have a recent figure, but you can kind of imagine this increases exponentially. There's a market replacement occurring. Those 1 billion bulbs, more and more of them are becoming LED technology. A lot of them are already fluorescent, but we're kind of skipping past the fluorescence, honestly. And then another issue, and this is kind of impacted, if you're old enough, this has kind of impacted market adoptance, is that LEDs are expensive. They actually require a lot of government subsidies to be affordable to the average consumer. And like around 2008, I'm pretty sure bulbs were like on the order of $10+ per bulb, which is kind of crazy. So now they're much less, and they're becoming much more affordable. Okay, so then this newer technology called filament LEDs, and if you guys have taken a chance to look at it as it comes around, it's kind of interesting. They basically, it looks like an incandescent. You have the tungsten filaments, except instead of tungsten, they have these little rods, and they put silicon on a glass substrate, and basically, and they coat that in phosphor. So when you excite it with electrons, it excites the LEDs, and then it goes through the phosphor, which makes it a yellow color, or a whiter yellow color. And if we look at the metrics for it, 800 lumens, which is the same 60-watt equivalent, takes about 5 to 8 watts. So if we compare that to the older LED technology, that is which was 8 to 12 watts, I believe, that is a decrease. And the lifetime is around the same, but it is greater. And we'll talk about that. Okay. So here's kind of some images. The matrix LED is probably what you're much more used to. You have an opaque plastic cap, and it has to be that way. Otherwise, the light would be too bright to look at. That's kind of it's a way to make it more, I guess, spread out, diffuse, more appealing to the eyeballs. Also, the bottom half of it is typically a very large metal heatsink, which if you've ever held one of these bulbs, they're fairly heavy. I think it's usually made out of aluminum. And then inside that heatsink is an LED driver, which kind of sits in the socket, and then these are where the terminals come out so that you can screw in. But it's important to note that this LED driver, because we are talking about LED drivers, the technology, but also the LED drivers. The LED driver actually has a pretty relaxed volume constraint. There's a lot of space in that heatsink for an LED driver to go in, and for an LED driver designer, you have a lot of mobility. I don't think that's the very most pressing performance metric in terms of like cost or power factor or efficiency. And then here's the newer type, and as you can see, it looks very like an incandescent, kind of what I described. But the reason that it doesn't require such a big heatsink is because it has a lot better thermal impedance, or a lot lower thermal impedance. So it can absorb heat much better. Actually, if you ever take apart one of these things for yourself and you turn it on, you let it sit there, the bottom of this guy, if you look at it, I don't think I have a detached one there, but the bottom of it's made of metal, and it is attached directly to that heatsink, and that heatsink gets really hot really quickly. Meanwhile, this thing, actually, you can touch it while it's on. It's kind of interesting. But again, what's most important to note about this is the LED driver has a much higher volume constraint, because it doesn't look good. It's all about aesthetics. It doesn't look good for a driver to kind of come into your glass bulb. So you got to try to fit it into sockets so people don't have to see it. Okay, so these are some of the performance metrics that me, along with some others, determined were probably the most pertinent. These are the ones that you want to keep in mind as you try to design an LED driver, and these were the ones that we're going to use as a basis for comparison between bulbs. So we have power loss, which is just power in, power out, power factor, volumetric power density, volumetric utilization ratio, which I'll talk about a little bit more, flicker, and then what's called luminous efficacy. So power loss is, as you all are very familiar with, I'm sure, is basically indicates how capable the LED driver housing is to dispel heat, basically. So if I design an LED driver I can make it 50% efficient if I wanted to, but if it's only 2 watts, that's only 1 watt of loss I have to deal with, versus if it's 10 watts and I'm 50% efficient, that's 5 watts of loss I have to deal with. So that's, I think, a very big indicator of, or a big driver of the technology of matrix versus filament. And you can also relate this to efficiency, but we chose power loss because it fairly compares different LED drivers that have different power levels. Second one is power factor. Power factor indicates how resistive the light bulb looks to the grid. And if you think about those 1 billion light bulbs, incandescents are resistive. Incandescent light bulbs are resistive. But as we start to increase adoption of LEDs, that's a nonlinear load. You're basically hooking up a converter there. And so you actually have to be conscientious about the control of that converter so that you're doing power factor correction. Here's an example. This blue curve, which I don't know if you can see the colors, but the sinusoidal curve is the input voltage of the grid. And then there's 2 different light bulbs. One has no power factor correction, so it has that giant current spike here. And the other one does have power factor correction, so it's trying to track the input voltage. And currently there are some standards in place, although obviously they're not enforced. Let's see. Yeah, so power factor standards exist for lighting applications greater than 25 watts. So like laptop chargers, not cell phone chargers, but not for consumer LED lighting, which are around 10 watts. But if you think of in scale, 1 billion 10-watt loads kind of adds up. So IEEE is definitely pushing towards trying to apply some standards to these LEDs as the years progress. It's also important to note that power factor correction implies a higher cost design, higher complexity, which is why it directly trades off with cost. Okay, so here's power density and volumetric utilization. Power density is just the ratio of power processed to component volume. But then we had another metric that we I guess made up. It's a ratio of component volume to the converter boxed enclosure volume. So what that means is if the component volume of my LED driver is, let's say, 1 centimeter cubed, but the enclosure is 10 centimeters cubed, I want to convey that through this ratio. So this is very useful for comparison between the filaments and matrix, because as I said earlier, the filament LEDs have a much higher, I guess a more strict volume constraint. And this volumetric utilization is what's going to convey that in a quantitative metric. This is the last metric that we're going to use. Is called luminous efficacy, and this is very standard. This one's actually not so much related to the LED driver, but more of the LED emitter technology. So that's like incandescent, fluorescent, matrix, or filament. As you can see, these are kind of the standards for. First, I should define it. It's basically if you have power in, how much light out do you get? So lumens is a SI standard unit. Or maybe it's candela, but anyway, for an incandescent, that's around like 20 watts per or lumens per watt, and then for the newer technologies, the luminous efficacy increases. And this is important because this is also heat dispelled. We only talked about heat. We've only defined heat loss for the driver, but there's also heat loss for the emitter itself. And then for kind of a comparison, 100% efficient emitter has around 700 lumens per watt. So, and actually another interesting point is filament LEDs do have significantly higher luminous efficacy. So that's kind of another thing going for it. Okay, actually, this is the last metric. So this one is perhaps the most important, and it actually has the most literature related to it. Flicker is defined as the periodic fluctuation in luminous intensity of a luminaire. So it's like getting brighter, dimmer, but it's happening at a very fast frequency. It has been shown in many publications that flicker can have a negative impact on human health. The lower the frequency, the worse the effect. So for the same amount of flicker. But what's interesting is regulations do not exist for luminaire manufacturers, although a standard was published in the last 2 years. As you can see by data that I'll present to you later, those standards aren't actually enforced, and it kind of makes me a little bit concerned about the LEDs that are currently in the ceilings above us. We define that as we can actually, because it's actually very hard to measure the luminous output or the luminous flux of a light bulb. We can use instead current, so we can measure the output current waveform and use that to calculate the flicker. And there's typically two components. There's the twice line frequency component, because this is a single phase system, so you're going to have a power ripple, and then you're going to have a switching frequency component. It turns out the switching frequency component doesn't matter, because as I said, the higher the frequency, the less effect it has on health, and it's been shown that frequencies above like 10 kilohertz don't have any impact on human health. So what we really care about is the twice line frequency component. So here's an example. The top figure is this is just a light bulb. Those are the input voltage and current waveforms. So there is some power factor correction because it's trying to track the sinusoid. And then on the bottom this is a 120, or like basically a grid time scale. And you can see there's about a 60% flicker modulation. And then this is at a 20 microsecond time scale. And this is at the switching frequency of 60 kilohertz. And there's a 7% flicker modulation. And this varies largely from each bulb. What kinds of, maybe sometimes this is much bigger than this. And yeah, it's interesting. Okay. So here's the test bench we used. Basically, pretty straightforward, but you just take apart the bulb. You have to be very careful how you do that. We found a way to take the filaments and not break them because we wanted to try to maintain the same thermal point as if the bulb was still entirely put together. Then you put 2 Yokogawas in just to measure basically all the input-output power waveforms. And then to do volume, actually a really good way to do that is to use immerse it in water and use the known density of water to calculate the volume of the exact volume of the converter, rather than trying to estimate components or the box volume or something. So here's a bunch of data. Like I said, there's 20 bulbs that we checked. A lot of what we chose, like I said, filament is newer. I don't know if you guys have even seen them before in the stores. But basically, what decided what we chose for bulbs was we found every single filament that we could on the market for this 60 watt equivalent A-type bulb. Those are all of them. There's no more. And actually, what's interesting is if you look at so here's the lumens. So there's around 800 for all these, but some of them don't get up to there, and we just kind of chose those for representative. But Philips, a really big light bulb manufacturer you've all heard of, they actually don't have a filament that exists at 800 lumens. Their highest one is 350 lumens. So this is still something, for whatever reason, industry is still struggling to make, I assume, cost-effective solutions, market-ready solutions. And then we found matrix bulbs that kind of correlated to each of the filament bulbs that we chose. So if we had a Westinghouse filament bulb, we found an equivalent Westinghouse matrix bulb, and that's just another point of comparison. So in this row, you can see the power factor. A lot of numbers, but you can kind of see that some of them are higher than others. Some are above 0.9, some of them are around 0.6. So that just shows whether there is power factor correction or not. This is the power density. Again, all over the place. Some converters were much bigger than others. And then here's the flicker. And this one might be a little bit more obvious. Some of them don't have any flicker at all. And this is at 120 hertz because that's what matters. Some of them don't have any flicker at all, and some of them have, I believe these are like 100% on here. At least there's one that's like 80-something%. I don't know where it went. Okay, and then here's plots of all the different converters. What's on the left of each is the converter itself, just kind of a top figure, and you guys kind of saw some examples. But on the right is what's called a spider plot, and that's basically a way to do a multi-dimensional plot on a 2D plot. So basically you plot radially outwards for each of these points. So here's power factor, and wait, I got one on the next slide. No, I don't. Okay. Power factor, power density, power, and you can kind of normalize between all of them, and you can see, kind of, in a way, compare different bulbs to each other. Okay, this is what I was talking about earlier about flicker. This yellow region is not my region. This has been defined from a lot of medical data. What is the negative, like where is the negative region of flicker versus frequency? And this doesn't actually depend on LEDs. It could depend on whether, like, any type of light. So any light, any flicker, these are the frequencies that you care about. And what's interesting is a lot of these bulbs are outside this region, and that's significant. There's actually, this is a low-risk region. There's actually a no-risk region that's like somewhere within here. So it's a little bit inside. But this is definitely, like, in a way, inexcusable. It is outside the low-risk region. There's not really any margin for error. That's just like, yeah, anyway. Take it as you will. Okay. And then here's just another example of a correlation between performance metrics. This is power loss versus power factor. And as you can see, you can kind of group these into whether there is power factor correction or whether there isn't, whether there is specific hardware and control that allows power factor correction or whether there isn't. Okay, some other metrics of interest might be what output voltage, because we didn't actually talk about that. The grid, whether it's 120 volts, 60 hertz, or 230 volts, 50 hertz, which is European, we didn't talk about the output voltage. And the output voltage depends on how many LEDs you have hooked up in series on the output, right? You can hook them up in parallel or series, all kinds of configurations to try to get the maximum amount of power out. What decides what that output voltage is? Color rendering index and color temperature have a lot more to do with aesthetics. That's not really our domain. We're not LED physicists, but that's what those metrics matter a lot more to consumers, because you get a lot of complaints about, oh, this bulb is slightly more yellow than was advertised. And then there's some more driver metrics for if you're doing LED driver design. So, like, what topologies do you choose? Turns out most of these drivers are buck boost type. There's not a lot of isolation. There's not really a need to, because you're not going to be able to touch the inside of the bulb. There's no safety concern there. Lifetime reliability, cost. Okay, and I believe that's it. Any questions?
Is there a bulb that satisfies your requirements across all the metrics?
So I don't actually have any requirements. I'm trying to see what the data is.
Yeah, but is there the one that satisfies performance across most of the metrics?
That makes me happy. That is an interesting point. I did look at that. So most of these bulb manufacturers dabble in the incandescent market. Okay, one of them that does not is Cree. You've probably heard of Cree. I don't know if they were a startup, but they came into prominence around 15 years ago with LEDs. Their bread and butter is LEDs. They don't touch any other type of technology, and they're trying to innovate in different ways besides that filament type. Most companies are going down this filament route, but they're trying to do, like, I don't know if you've seen these really fancy, like, donut structures and stuff. Like, you can look them up. I should draw one. So, like, rather than having a circle like this with all the chips on it, they have basically a tower. It's like a cylinder with aluminum, and they have the LEDs on, like, the sides and, like, all the way around it. And that's another way they're trying to solve for the problems of the matrix LED, but try to still maintain competitiveness. But the reason I bring this up is because Cree has, I think, some of the highest power factor. There's some other things going for it too. That was one of the ones that stood out to me. But I do think it's interesting. Sure, matrix has been around longer. It's a much more mature technology, so it's probably a better decision. You're going to have a bigger converter, so that means that there's more room to try to handle flicker. Because flicker basically has to do with how big your electrolytic capacitor is. The more volume you can spare, the bigger that cap can be. The filament, that space doesn't exist. If you saw what I handed around, it's very tiny electrolytic. I'm pretty sure, well, actually, some of the flickers are handled very well. So, I don't know, take it for what you will. If you want the data, I can send it to you. You make your own analysis. But there's so many more light bulbs outside of this one. Like I said, this is basically all that exists for filament, and these were chosen to match these. But there's a ton more of these. What's up?
So I see most of the LED bulb with really poor power factor will have. So if you buy one,
Yes.
what is the reason for that?
Okay, so if you're familiar with, like, here, let me draw this on the board, although this won't even look very good. Okay, so if you're familiar with power DC equals power AC, right? So there's like a fundamental power, instantaneous power difference on a single phase converter. And you have VDC, IDC equals VAC, IAC. And what you end up with is some constant power equals some constant power plus a twice line frequency component, so like 2 omega t. This is only applicable when your AC voltage and current are sinusoidal. So if you're not doing power factor correction, the less and less that this applies to you, if that makes sense. So the input the AC voltage is sinusoidal, right? That's the grid. If you're not doing power factor correction, this isn't sinusoidal, so you're not going to have this term. So the less power factor correction you do, so the power factor correction doesn't have anything to do with whether we can buffer it or not. It has, well, that has to do more with like volume. It has more to do with what's useful for the grid, right? So like I said, there's 1 billion bulbs. If all those became LEDs today with the existing, like if all of them were 0.6 power factor LED bulbs today, that would be a problem. That'd be a significant problem. That'd be injecting a ton of current harmonics into the grid. So standards have to exist to enforce power factor correction in these light bulbs. Since, well, once that will happen eventually, once power factor correction is enforced on light bulbs, then you start to have this problem. And so then you're going to have trade-offs with volume. Does that make sense?
So does it mean that when we enforce a power correction, the light bulb will be worse for our health?
So, yeah, I guess so, yeah.
Well, that doesn't sound good.
That's an interesting, yeah, you're putting it very frankly, and there's a lot more subtlety there, but yeah.
But as long as it is in like low risk region.
Yeah, no, yeah, that's, within here, basically anything within here is only going to affect like epileptic seizure patients. Outside of that, you're going to probably affect that modern person. What's up, average person? Yeah, no, that's why there's a no risk region. That's kind of, I gave these manufacturers the benefit of the doubt. I tried my best.
So I have 2 curiosities. One, for incandescent and CFL, how is flicker? I imagine incandescent is fine. Like,
So flicker doesn't exist in incandescent because I think the word for it is like we'll be out of here in 5 minutes. There's a thermal time constant. So like, it's like a luminous time constant, I guess. Like you put a current through the incandescent.
it doesn't cool down enough.
Yeah, otherwise you would see like the light would do this, but instead it does something like this. Like it's filtered in a way, right?
For CFL?
So that problem does exist, but that's what electronic ballasts are for, is they control the current going in.
And then if you have multiple independent like LED lights close to each other, would their flicker balance each other out, or does it still mess with us? It's probably a question for a doctor, not an electrical engineer.
Be on the same grid.
Yeah, no, it's not going to impact the grid, or it's not going to help. It's not going to. You're asking whether it's going to like constructively or destructively interfere, right?
Yeah.
So if we look at this guy, they're going to be constructive. So like if you look at this spike, all those spikes will just add to each other. Yeah, there's no wiggle room.
Brains that operate slightly differently, maybe.
Yeah, but like on the there's no way to shift the phase of the grid. On the DC side, it's very difficult to say what where the switching frequency phase will line up. So you might get cancellation there, but you're not canceling the DC side anyway. So yeah, it would not help.
Okay.
I don't think there's any scheme that would work. What's up?
So from a circuit topology perspective, you looked at so many elements. How do they differ from circuit topology perspective? Are there any interesting circuits?
Okay, so that is still something I need to do because it takes a lot of time to determine the topology of these little guys. I've done most of them, let's say like 60% of them, and I think of what's that?
Do they come up with individual circuits, or do they have one parent circuit and they can derive from there?
They are all, basically 90% of them are buck boost topologies. And a lot of that has to do with what the output voltage is going to be. I guess, let's see, do I have data for that? Okay, so this column right here is the output voltage. And depending on whether, like the AC is obviously 120 volts RMS, this decides whether you have to boost or you have to buck boost, right? Because at different points of the line, you either have to step up or step down. So some of these, like this one, is 200 volts output. I believe that's some type of boost converter. But all the other ones are buck boost because.
This voltage is dependent on how many LEDs they put in string.
So that more has to do, and this is where, like, you can imagine in a company, you have all the different groups talking with each other, communicating. LED, the people designing the LEDs, the actual LED emitter, so like designing this part of it is saying, oh, this is the voltage that we're going to make, because there's certain parallel series combinations that it's going to give us the right light output that we want. So go power electronics designer, you have to design a converter that has this output voltage. But I think mostly it's going to be somewhere where it has to be a buck boost. It has to be both.
And in buck boost topologies, are there like standard buck boost, or what kind of topologies are there?
So this is where I can't answer because I don't know. There are some very unique things. There's a lot of like, all of them have like inrush current limiters. Actually all of them are analog control. So that's going to impact like some side. Yeah, I guess I could draw. So like typically you think of a buck boost with a switch up here and an inductor and a switch up here. But some of them have like the switch on the bottom, like and that has to do with the gate driving and all that. We can talk about that more, but like each one is very different.
Let me ask you one higher level question. How are you attacking when you're trying to debug how the circuit is? How are you approaching to figure out what the circuit is?
I look at every node, I look at every wire and see where it connects and try to draw out the circuit. Because there's so many different components. You can kind of guess. For instance, it's very hard to tell whether it's an inductor or a transformer, just looking at it. You have to look at how many leads are coming out of it.
Do you get the specs of the components as well? Like
No, I do not. Because some of them don't even have data sheets. Yeah. But yeah, I'm trying to gauge from like basically my knowledge of circuits and topologies, what is, if there's a blank here and I see a component, is that the FET I'm looking for, or is that some type of gate driver, current divider? Yeah. It's not easy, but I'm working on it. Yep, let's get out of here.